So this week's lab is to measure the index of refraction of water versus air. Now, just a little bit of background. When we talk about waves, waves travel, the speed of a wave as it's traveling through a medium is controlled by the medium. The same holds true for light waves. Now, the fastest speed that a light wave can travel is when it's traveling through a vacuum. We have this term n, which is the index of refraction, which is equal to the speed of a wave in a vacuum over the speed of the wave in the medium. This is also equal to c, the speed of light, 3 times 10 to the 8th meters per second. What we wanted to try to do today is to try to measure the ratio of the speed of light in water, find that value for water and air. Now, air is, for most of our purposes, is about the same as it is in vacuum. It is slightly different, but for most purposes, we can say vacuum over air is going to be equal to 1. So n air is equal to 1. Now, as waves travel from one medium to another, they can speed up and slow down depending on the medium. If that wave hits the boundary between the two medium and it's not perpendicular, what will happen is the wave will bend. You've seen this phenomenon if you stick like a spoon in a glass of water and it looks like the spoon is bent. That's because the wave is bending as it goes from one medium to the next. What we want to do is try to get that measurement. It's based on a formula called Snell's formula, which you see in your reference table. It says n1 sine theta 1 equals n2 sine theta 2. Whereas n1 and n2 are the index of refraction for the two different medium. The sine theta 1 would be the incident angle, sine theta 2 would be the refracted angle. So if I have a boundary between two medium, we always measure our angles from the normal, so this is the boundary. This would be a light wave struck here. We would draw a line perpendicular to the boundary. This would be our normal. And if this is the incident ray, this would be theta I, or the angle of incidence. When it goes through the boundary, it's going to bend depending on the change in speed. It can either bend towards the normal or away from the normal. And then this would be theta R. And these numbers are plugged into these equations, and the amount that it bends depends on the ratio of the speeds that are changing. This week we want to try to take some measurements to measure between air and water. So what we're going to need to do is measure how the light rays bend as they go from the boundary between air and water. So we're going to do that by trying to trace the rays by using this little semicircular tray, which we're going to fill with water. We're going to put it on this sheet, which shows the semicircular tray, and there's a bunch of arrows, lines, which measure, if this is the boundary, this is the normal, these angles are measured from the normal. They're going to represent the light rays as they're traveling through water. We try to observe what happens to those rays as they go from the boundary between the water and the air. So what we're going to do is take our lab sheet, put it on a piece of cardboard. We're going to take our tray, put some water in it. Don't fill it all the way up to the top because the water will spill and get your paper wet. If you do spill some, it's okay, don't worry about it, but try to minimize that. And you place the tray on the sheet. Also, you need to have enough water in there so that you can see through the water. You have to make sure you're looking through the water and not the air. And the way we're going to trace the rays is we're going to take 3 pins. One pin is going to go at this, I'll show you on another lab sheet, this point where all the rays meet. Another pin is going to mark off the different rays, and then the third pin is what you have to find where, as the light ray emerges from the water, it goes into the air. So I'm going to place this one pin over here. I'm going to start from the first angle, which is 10 degrees, and place the pin on that 10-degree line. Now, if you can bring the camera over. What we're going to do is to try to show you what the camera lens is going to try to represent your eye. So, do you want to put that on the camera? we're good. And as you can see, right now, all right, get this a little bit. If I come down right here, you can see the two pins in the thing. But what you want to do is line up your eye. In this case, the camera lens is the eye. And so what we're going to do is move your eye around until the two pins line up. So it looks like the one pin is directly in front of the other pin. Okay, and if you can see that here, right now it's off a little bit. Okay, so now they're lined up so one pin blocks the other. I'm going to take a third pin, go behind the tray, and try to line that pin up with the other two. So if you can see this tray in the water, behind the water, I'm going to just slide it over till it looks like it's all in a row with pin 1 and pin 2. If you look at this from above, you should be able to see that they're not all lined up because they're not really lined up. It just appears that way when you're looking at it through the water. So what we're going to do now is then, I put this hole in the paper. I'm going to take your pencil and just note the angle that it started from. So the first ray was on the 10-degree point. So I'm going to label this 10 degrees over here. Then you're going to continue along to see all of the other pre-drawn lines and keep going until you can't see it anymore. I'm going to skip a couple just for time, but so I'm not going to move this over to the 20-degree line. Remove the third pin. Now do the same thing. Move your eye so that pin 1 is directly in front of pin 2. And again, do the same thing. Take the third pin, move it along. Behind it and label it. That was on the 20 degree, so I'm going to label that 20. Continue along. I'm going to skip the 25 and go to the 30. Do the same thing. Just keep moving my eye until I get the front pin and the back pin, pin 1 and pin 2 lined up again. And then look for the third pin in the water. That down there, that's on 30 degree. Label that 30. And then you're just going to keep on doing that until it's going to come to a point where you can't see the pin in the water anymore. And if you see that, that's okay. You can just stop at that point. Once you finish that, if you can just take you can take the tray off the water. You see I spilled a little bit, but that's okay. Now what you're going to do is remove all the pins, put them back in the container on the table so they don't get lost. And then now what you need to do is now measure these angles. So we had the ray traveling from water and it went into air. You take a ruler, find the point here, and just connect from that center point to the hole, the pinholes in the paper. So now we have, this is the line that started from the 10 degree, this is the started from the 20, this started from the 30. Now those angles aren't going to be the same. If you take your protractor, place it on the paper, and now measure those angles and fill in the data table. So the angle in water is 10 degrees. If I read on the scale here, it came out to, get this lined up right, it looks like it's about 11 degrees. The one that I had on the 20 degree mark, that's about 25 degrees. And the one that's on the 30 degree mark, that looks like it's 41 degrees. Now don't go by my numbers because I'm just doing this quickly and I'm not really being real precise. So just don't copy mine and think it's the right answer. So now you have these things. Now, if you go back to the formula, it says N1 sine theta 1 is equal to N2 sine theta 2. We're trying to solve for, if we change those to air and water, gives us, say, N water times the sine of the angle in water should be equal to the index of refraction of air times the sine in air. So if I rearrange this so that I want to find this number, so if I rearrange this, I'll make sine theta in air is equal to NW over NA times the sine in water. So if this is my y variable, and this is my x variable, if this is the case, I should get a best fit line, and this should be equal to the slope. So the slope would be the index of refraction of water divided by the index of refraction in air. But since the index of refraction in air is 1, the slope will effectively be your index of refraction in water. So what you now need to do is come back to the sheet here, and since the graph is not based on the angle but the sine of the angle, you need to calculate the sines of all these angles you just measured and fill it in this column over here. The sines of the angles that were pre-drawn are already done on the sheet for you. And then all you need to then do is sine theta in air is the y variable, sine theta in water is the x variable. So you're going to take, this is the water, this is going to be the x-axis, this is water, this is air. So you make a graph on the back. You have a graph paper here. Make a graph of sine theta in air on the y-axis, sine theta water on the x-axis. Plot those points. Just make sure they come out. If it looks like it's a best fit line, it looks like it's linear, draw a best fit line. Find the slope of that. That will be your measured value for the n in water. Compare that with your expected value for n in water. You'll be able to find that on your reference table. And that's the lab.